A half-inch diameter water pipe is 60 feet long and delivers water at 5 GPM at 20 degrees C. What fraction of the pipe is taken up by the entrance length? So as we look at this, we're going to solve our entrance length equation, but before we can do that, it comes down to the big question. Laminar or turbulent? And that's going to really drive how we solve this problem. Once again, like all of our piping systems, one of the very first things that we're going to have to do is figure out what's the Reynolds number so we can figure out if we've got laminar or turbulent flow. So let's start with that. We're going to need to calculate our Reynolds number based on diameter, and we will calculate that using velocity diameter divided by kinematic viscosity. So the first thing that we'll do with this is we'll just go, we've got water at 20 degrees C. Let's go look that up. So if I go into my book, I look up kinematic viscosity 1.09 times 10 to the negative 5 feet squared per second. So I have velocity and diameter. Once again, 25 GPM is not a velocity. That is a volumetric flow rate. So we need to calculate out what's my volumetric flow rate. So how do I calculate volumetric flow rate? Well, Q is equal to V times A. So V is equal to Q divided by A. So as I take a look at that, though, I've got 5 gallons per minute. Typically, for our volumetric flow rates, we're going to want cubic feet per second. So we need to do some conversion. So 5 gallons per minute. We need to convert that over to feet per second. If you look in your equation manual, nifty conversion factor, 0.00223, and that will convert you cubic feet per second from gallons per minute. And so we plug that together, 0.0111 cubic feet per second. Now we can go back to our equation. So V is equal to 0.0111 cubic feet per second, and divide it by the area. So pi over 4 times 1/2 inch diameter, so 0.5 inch, but we need to convert that over to feet because we have feet on the upper part. So 1 foot is 12 inches, and that will give us our feet rating. Take that whole thing, square that, and so now if I plug this into my calculator, inches cancel, I've got feet squared, 1 feet will cancel, so I have foot per second, which is what I expect. My velocity through this pipe will be 8.17 feet per second. Now that we have velocity, we can take this guy here and plug in back into my Reynolds equation and calculate out my Reynolds number. Let's bring up a clean sheet of paper. So our Reynolds number based on diameter is going to be our velocity, 8.17 feet per second, times our diameter. Once again, it's dimensionless parameters, so we have to make sure that we convert that. 1/2 inch times 1 foot divided by 12 inches. So that takes care of V times D. We're going to divide that by our kinematic viscosity, 1.09 times 10 to the negative 5 foot squared per second. So once again, let's just check the units. Inches cancel. I got a foot squared here, foot squared there. I've got a second. Everything cancels out. So this is a dimensionless parameter, which is great. That's what I expect. 31,300. This is a turbulent flow. Just remember, we only need it to be above 4,300, so we are a fully turbulent flow. So now if I go and I calculate out, okay, what is my entrance length? Well, we have LE over D. For turbulent flow is going to be 1.6 Reynolds number to the 1/4. So Reynolds number based on diameter. So if I go and I calculate that out, I've got 1.6 times 31,300 Reynolds number raised to the 1/4 power. So LE over D is going to be 21. So 21 is You can look at it with a 1/2 inch. You can do it one way and say, okay, well then that means my entrance length is 10.5 inches, because that's 21 times the diameter. So now I want to know what fraction of the pipe is taken up by the entrance length. Okay, well I have my entrance length. I'm going to divide that by my pipe length. So 10.5 inches. My pipe length is 60 feet long. Got to make sure that I have the units to work out here, because I should have a percentage, so it's unitless. So 60 feet times, I want it in inches, so I've got 12 inches per 1 foot. And that's going to give me, the feet will cancel, the inches will cancel. I'll end up here with a decimal. And so if I multiply that out, I should get 0.015, which is 1.5% is the fraction of the pipe that's taken up by entrance length. Why is this important? Because if we're doing solving on this pipe system, we can sit there and go, 1.5% really isn't that much of the pipe. Since it isn't that much of the pipe, we're just going to assume that the entire pipe is a fully developed flow. And because of that, all the stuff that we're going to learn with calculating our head loss and stuff, we can just apply it to the entire pipe. Is it exactly correct? No. But since it is such a small percentage of the problem, it's really almost a rounding error at that point. We're going to be really close to what we're doing. It's kind of like when we're dealing with large tubs and large surfaces of water, and we say, well, we're just going to assume the velocity is 0. Is it really 0? Not really, because it is slowly going down in the y direction, but it gets lost. The amount that adds to the problem, it just gets lost in the noise, because it's not really going to have a major effect. Just like with this pipe here, 1.5%. It's not going to have a major effect on the pipe. If this pipe was 12 inches long, it would have a major effect on the pipe, because 10.5 inches would be taken up by entrance length, and you'd only have 1.5 inches that was fully developed.